Hello, welcome to week 8 where I'm going to walk through chemical compounds and emerging contaminants. I've got 20 slides and I'm going to move pretty quickly to a streamlined week so that you can focus on your term projects. We're going to talk about pesticides and then pharmaceuticals and personal care products, sources, movement, and quantification in the environment. We'll start with talking about pesticides a little bit and then move into the PPCP realm, which is a little bit more on the emerging contaminant side. So I want to thank Troy Botter at Colorado State University for a lot of material presented in these slides. If we think about pesticides, this is part of a presentation often given to applicators on the farm, thinking about the pathways that it can reach groundwater or surface water. And there's a couple of key attributes. Volatility is really important for people applying movement in the air. Solubility, adsorptivity, and persistence are really important for thinking about water. And solubility, obviously, if we've got things that are more soluble, then they're going to be more likely to move with water, and especially into groundwater. If things are tied up with sediment, then they could still move into water associated with that sediment. Sorption is another really important characteristic of pesticides, which is their affinity to be attracted to the soil matrix by the positive or negative charge locations on the soil matrix. And the sorption index, so a high sorption index here means that they're likely to be sorbed, and for a couple of different chemicals here, those sorption numbers are given. And so these with the high sorption potential are going to tend to stick to the soil, and they're going to have lower risk of leaching sensibly. Pesticide degradation is very important to think about. So how long does it take to go from a new molecule through a biological or chemical or photo degradation process to get to the daughter products, or things that are no longer as effective as the pesticide? So we tend to think about that in terms of half-lives, or the number of days it takes before only half of the product is left. And you can see we've got a range of half-lives here from 14 days to 500 days. And obviously those that have shorter half-lives are going to be less likely to make it into water if we're only considering that attribute, because they're going to break down. A number of things can affect the degradation rate of pesticides, or the half-life. And here we see depicted half-life on the y-axis here for two different chemicals, and low and intermediate and a higher soil moisture, and we can see that the half-life decreases with increasing soil moisture, or at the low soil moisture, the chemical is going to persist for a long time. As you get more soil moisture, conditions are more appropriate, more conducive to degradation, and they will break down faster. But you can see there was a large difference in that effect between these two chemicals, so chemical specific. So we can think about these different characteristics in terms of their risk for leaching and risk for runoff. And so dicamba salt doesn't sorb well. It's got a really low sorption coefficient, but it's very soluble, and so it's really likely to leach, but it's not very likely to run off over the surface as particulate. Whereas benomyl has a high sorption capacity, is not very soluble, so it's not likely to reach, but it is likely to run off as adsorbed to sediment. So based on these characteristics, there are herbicides with groundwater or surface water advisories in their environmental statements. And here's a list of those. I'll talk a little bit more about those advisories in just a second, but we can think about, from the hydrology lecture and this graphic that I've used to talk about the framework of thinking about pathways of overland flow with particulate and soluble components, or subsurface flow for contaminants to streams that is just the soluble component. So a useful thing to know about are environmental advisory statements on pesticide labels, and here's an example of one, and you can go find these at this website. Is a commercial website that has a number of manufacturers represented. You can search for a brand name of a pesticide and then look at the pesticide labels for those. And then the way that I searched was simply to go into the web browser's find feature and search for the words groundwater, or the word groundwater, one word, and then surface water, two words, and was able to find these for a couple of different chemicals in this list that we just looked at. So I looked up a couple of these different names and then found their advisories. So that's an effort to educate people, applicators especially, about the different risks for environmental problems associated with different chemicals, and so they can make wise decisions about how and when they apply and where, on what types of sites. And so there are a lot of site-specific conditions that also affect whether the risk of chemicals getting into water resources, and soil properties are very important. Soil organic matter, clay content, pH, and moisture are all soil factors affecting absorption of pesticides. And so low organic matter and low clay content are going to mean less likely absorption. And so clay is really good at absorbing things, as is soil organic matter. So if you've got high content of soil organic matter and clay, likely to retain those pesticides on the soil, give them time to break down before they have a chance to be mobilized into water resources. If there's going to be a risk for chemicals to move into water, then there's got to be water moving. And so if you're in a very arid environment without much movement and recharge of groundwater, probably pretty low risk of groundwater being contaminated there. In a system like this, you do tend to see storms that produce a lot of runoff, so if you were controlling weeds in a very arid environment like this, you might want to be thinking about doing it when you weren't going to have precipitation causing runoff with pesticide absorbed onto sediment. Irrigation can definitely increase the amount of water moving down and recharging groundwater. So sprinkler irrigation, we tend to have better control over and could not over-irrigate and not send too much water down. Whereas flood and controlled floods or gated systems like this, you tend to put more water down, and so thinking about that and your water balance, basically, how much water are you putting on, how much evapotranspiration is going up, what's going down versus running off the surface. That water driver is critical for understanding whether chemicals are going to move. And obviously, when we think about groundwater, the depth to groundwater is important. In systems with very shallow groundwater, there's a higher risk of chemicals reaching groundwater. In systems with very deep groundwater, it's less likely that it's going to make it, or the time frames on which it's going to make it down there are much longer. So all of this type of information is critical for managers to understand risk and for applicators to understand risk, and so they can affect their management to try and reduce problems. And so a high-risk situation would be sandy soil, low organic matter, lots of macropores, so large pores to convey water downward quickly. Pesticide with a long half-life, it's got low absorption and high solubility. This is a recipe for contamination of groundwater. So if we're thinking about risk, again, to sum this up, leaching, the overlying soil type, depth to the water table, geology, and recharge rate are all important for thinking about contamination of groundwater. For runoff, thinking about slope, soil type, less well-drained soils like clays are going to send water over the surface, conditions of the soil, their macropores, what's the rate of irrigation, what type of vegetation do you have, all of those things that we talked about in the sediment lecture, producing runoff, and those are going to, so those two categories of considerations are going to affect what type of water movement you're most likely to get. And so whether you could, what type of water resource vector you've got. And so then we can start thinking about how we would monitor that, or how we would monitor that or affect management changes to reduce the risk. It's interesting to note that the majority of very high detections of pesticide in groundwater come from point sources. Problems with storage of chemicals or problems with mixing And so when things are mixed, there are a lot of precautions that applicators should be taking to avoid back siphoning chemical down into a well or causing spills near a wellhead where you've really got that increased avenue of water moving down into groundwater right there. So transitioning to pharmaceuticals, hormones, and other organic wastewater contaminants in U.S. streams, this really early paper in 2000, this is a fact sheet talking about a USGS study, and this is your only required reading for the week that just overviews that paper and the findings. And a lot of work has happened since this time, and there are a lot of papers out there that you'll have an opportunity to find this week and summarize something that you're interested in surrounding this topic. So some of the big hitters here were steroids, detergent metabolites, and plasticizers in this USGS study. So pharmaceuticals and personal care products, often referred to by the acronym PPCPs, are any product that individuals will use for personal, healthcare, cosmetic reasons, or agribusiness to enhance the growth or health of livestock. And these include things that people take over the counter, vet drugs, fragrances, cosmetics, sunscreen, bug repellent, things like that. And drugs that are taken are not completely absorbed by the body of humans or animals, and so are passed on through wastewater into surface water. So in the case of humans, we take a lot of prescriptions for a variety of things. We're a very well-medicated society, and those can pass into groundwater or surface water through our septic systems or through municipal treatment systems if they're not removed completely. And in the case of animals, if animals are given antibiotics or other medications, then their waste similarly is at risk of transmitting those things into ground or surface water. So thinking about humans in this pathway, there's a supplemental reading up that has this table in it that shows you the percentage excretion of the chemicals unchanged, and many of these, 80 to 90%, greater than 60% of these chemicals that make it through the body and are excreted unchanged, meaning that those pills that you take are transmitting a lot of that chemical into wastewater. And this is something that we can't really help, but one thing that we can help that's important to note is disposal of unused prescriptions, and those things should never be flushed down the drain. They should be packaged according to local recommendations, maybe gotten a little bit wet so that they're not attractive anymore for somebody to take if they find them, but then packaged in a couple of bags and put into the local landfill. And in this paper by Hirsch specifically, they were talking about runoff of antibiotics, and in cases where we are discharging large quantities of antibiotics into surface water, we are definitely producing resistant bugs which no longer respond to antibiotics, which is a big problem for medical treatments. Hormones are something that we take. Women taking birth control pass a lot of those hormones through their body, and the result is definitely showing up in aquatic ecosystems. And this paper is also a supplemental reading you can take a look at about the feminization of fish, in this case in Britain. Another topic I want to touch on in this vein is chlorination disinfection byproducts. And so I mentioned this first in the nutrient lecture where we talked about increased organic carbon in surface water as a result of nuisance algae growth. And when we get a drinking water treatment plant that's pulling from a surface water source, they treat for particulates and then filter, and then they have to disinfect to deal with the microbes, the waterborne pathogens that might be in there. And while they've taken out the particulate carbon, the chunks of algae, they have a hard time removing the dissolved organic carbon, or the DOC. And then when you add chlorine to disinfect and kill the waterborne pathogens, it reacts with the DOC and you get chlorination disinfection byproducts. And these are something that we have known about for some time, and so there are drinking water standards associated with these, and you can see those listed here from the EPA's maximum contaminant level list. So we've talked about a couple of different types of compounds here, and one thing, while these disinfection byproducts do have standards, a lot of the hormones and pharmaceuticals do not have standards, and even in the case of these, I and other folks have to wonder, what are the compounding or synergistic effects if we're exposed to low-level concentrations of all these things all the time? And one thing that silly that comes to mind to me is from the Batman movie where Joker put the different compounds into a number of different cosmetics, and you had to get a combination of them before you had the effect. I don't know if anybody remembers that, but kind of a silly parallel. So thinking about, similar to how we talked about it in pesticides, movement in soils is something we can think about for pharmaceuticals as well. And the USGS had a study in Colorado in 2003 where they looked at use of reclaimed water for irrigation. And so they did soil cores to collect samples over 3 different months at a couple of different sites and tested for 19 pharmaceuticals. And I wanted to go back and look at this paper, but unfortunately all of the USGS publications are not available during the shutdown, and so that is a limitation right now. But one thing that we can see is that they looked at water solubility and a octanol water partition coefficient. So solubility is a pretty self-explanatory term, and compounds with higher solubility are more likely to move through the soil and get into groundwater. That is inversely related to this octanol water partition coefficient, which is basically a test where you put a compound in a mixture of octanol, which is a fatty. It's not a fatty solution, as opposed to water, and you see whether the compound wants to be in the octanol or in the water. And so if it goes into the water, then it's water soluble, and if it tends to be in the octanol, then it wants to accumulate in fats of people or organic matter in the soil. And so these two things are inverse here. We can see that very soluble compounds have a very low octanol partition coefficient. And so this paper talked about the importance of that in their findings, and again, I wish that we could go back and look at that in more detail. So just a little bit about sampling for pharmaceuticals and personal care products. The concentrations for these things we're looking at are extremely low. And so Tyvek suits and lots of precautions, not putting any fragrances on, and being careful about showering the day before sampling, and the soaps and the detergents that you're using, all of those things could give you false positives. And so these suits and a lot of caution are critical. And that's because we're expecting these things in such low concentrations, and the detection limits are very low. And this is out of that USGS pub, and actually there are not units here, but there are we're talking parts per trillion, parts per billion, and parts per trillion that we're looking for in these things in a lot of cases. So I want to wrap up this lesson in the context of the course objectives, and we've hit 7 of the 8, I think, are relevant to this topic. And so your discussion is going to ask for you to find a paper and talk about at least one of these course objectives in the context of that paper. Legal framework, you can see the EPA's maximum contaminant level list. You can just Google that and find that list. And again, we've got health standards for pesticides and a lot of chlorination disinfection byproducts, but not for personal care products. But on that topic, you can look up the EPA's contaminant candidate list and find out what they're doing to review emerging contaminants and think about setting Safe Drinking Water Act standards for those. So that's in the context of the legal framework. Surrogate variables, this is something I'm not really aware of a lot of options for looking at surrogates for pharmaceuticals and personal care products. Actually, caffeine is a product that is often used as a surrogate for other things, for wastewater influence. So I guess that would be kind of a reverse option for looking at something there. Temporal variability, I have not seen studies really in the variation of personal care products through time. So that could be something interesting. pitfalls for monitoring. We talked about the Tyvek suits and the very low concentration, so analysis is very expensive. So pitfalls for monitoring, course learning objective number 5. I will note that the one objective we're missing here is dimension analysis, which isn't really relevant, I don't think, to this week. But if you want to try and bring that in some way, then you're welcome to. Impacts, we talked about documented impacts on aquatic organisms, and a lot of the, for some of these compounds, the disinfection byproducts, the human health effects are known, and so the standards are set. But for a lot of the new compounds, the effects are largely unknown, and so setting standards for those is going to be challenging. 7, moving through watersheds, so understanding how that happens. So we talked about the sources, vectors, so is water moving? Is it moving over the surface or through the subsurface? And how mobile and persistent are the chemicals? So that's all the solubility, sorption coefficient, and all of those things that we just talked about. Data sources. Pesticides, I believe all states have a pesticide program. I know at least a handful of the states that I'm aware of all do. And this is a link to the Montana webpage where they have a map of a regular network of wells that are tested for pesticides. And so I think a lot of states use tax off pesticide sales to fund those type of programs, and be interesting to see whether all of your states have that type of program as well. And as far as personal pharmaceuticals and personal care products, a lot of this data, as far as I'm aware right now, is in specific project reports, because it is still fairly new, and so there hasn't been a whole lot of centralization of the data, although USGS has done some of that work, and hopefully before long they'll be back to work and that web page will be back up and we'll be able to look at those things. So again, we'll outline it in the discussion, but basically if you will use Web of Science, search and find an article, pretty wide array of options here, just anything that falls into the context of personal care products or emerging contaminants or pesticides, and think about and address one of these course objectives in your synopsis of that paper's findings.